Dr. Abhishek Majumder got his PhD in statistics at University of North California at Chapel Hill, and at
Carolina,
2000,
North
what?
Carolina.
North Carolina. Okay, sorry. And 2015, when I was starting my PhD at University of Copenhagen, I think same day or maybe with 1 day difference, he was starting a postdoc at University of Copenhagen. So we were in same place for I think maybe 2 years. And then after that, he worked in several different countries, Sweden, Singapore, and now UK. He's going to talk about long-time behaviors of some regime switching process. Dr. Majumdar, please go ahead.
Yeah, thank you, Amit. Thank you for inviting me. So I initially I had thought about presenting a different talk with different abstract, but unfortunately for because I was working on on that paper with someone, and there are some results that needed more work. So I thought I should present this work, and I'm thankful to Amit that he allowed me to present this one. So this is a work that I have been doing for some time, which is related with long time behavior of a some type of stochastic processes. So let's begin. I'll explain each of these term and then I'll go to the problem. So that will be the structure of the presentation. So, right. So in real life, in data science, in statistics, we we deal with time series data, or we deal with data that you observe over time. And suppose the data, data is represented by this form called Y, and for every time you observe YT. Now, for studying that those kind of time series or stochastic processes, you can think that this YT evolves, or this data sequence evolves in the following manner, that it will be a function of the function is psi, the function of some parameter theta, and then there is a time index. So, that function can be deterministic. In that case, there is nothing random in it, but usually the function is random, and we study how random component affects the long time behavior of the process YT and so on. So that is usual time series that we see. But certain times what happens that instead of having this uh, the parameter theta fixed, we can think that this parameter changes over time, and that is driven by some underlying time series or stochastic process, which is defined here as, or which is represented here as xt, where xt takes value in some finite or countably infinite state space S. So xt is called the regime process because xt denotes the regime that x takes at time t, and set of all possible regime is called S. So for particular regime I, your time series, original time series will behave as yt equal to psi of theta I, comma t, and so on. So what happens that as xt changes its value over time, the the original process yt, it will fluctuate over time. So now the question that I would like to answer, and it is a natural question for anyone to answer, that this how this underlying process or this underlying regime process X, that or the parameters of this underlying regime process affect the long time behavior of Y. So if we try to have an example, so you can think of an autoregressive process, which is discrete time series, where you know that autoregression coefficient, we usually always the autoregression coefficient is always strictly less than is equal to 1. So it can take value less than 1, equal to 1, or greater than 1. So if it is greater than 1, then it will diverge. If it is equal to 1, then it will have a wiggly behavior. If it is strictly less than 1, then it will be a stationary process. Now, what happens that instead of the autoregression coefficient have being fixed, if it changes its value from in some regime it is strictly less than 1, in some regime it is strictly greater than 1, then how the regime switching dynamics will affect the long time behavior of the overall process. So that is the usual bigger question that I would be trying to answer. So why it is important? Because in real life data in various time series, for example, interest rate modeling or volatility studying, volatility of stochastic models, we observe this Y, and then based on some parameterization, we try to have some iterative methods to compute the estimate of the parameter, this theta that we have seen earlier page. And also under certain strict assumption, it is possible to also compute the estimate of the parameters that drive the dynamics of xt under some Markovian assumption or other assumption. Now, what happens that when you are trying to answer that how these how for large x how the in the time t going to infinity limit, this probability of yt greater than x, this kind of exceedance probability will take, and how that probability will depend on the underlying dynamics of xt. The reason it is important, because suppose you are trying to work in a Wall Street or some financial organization, and you studied some interest rate data, and suppose your stakeholder asks that, okay, so here is a stable regime and here is an unstable regime, and we can see the switching parameter value. Then if the switching value changes from 0.5 to 0.6, then how that will affect the long-term exceedance probability of this. So in order to answer such question, it is very important to have a concrete form of that value. So that is the reason why exact long-time behavior is important for YT, so that we can study this kind of value exactly and how that depends on the underlying regime switching dynamics. So if I take a very simple example, so I talked about autoregressive process. Here it is a continuous time version of the autoregressive time series that we talked about. It's called the Ornstein-Uhlenbeck process, where you have the origin. I mean, you have the simply ddt of y is equal to minus a dt. But when you are writing that in a stochastic manner, you have a noise, and that is here mentioned in terms of a differential of a Wiener process. So if what is the Wiener process? Wiener process is basically a stochastic process which has a stationary and independent increments that starts from 0, and each increment has the distribution that has a normal with mean 0, and variance is the length of the interval or the increment. So that is how Wiener process is defined. So you can write this stochastic differential equation in this form. And if I use a very basic Ito's lemma, then one can get a expression that is like this. Now, if I study this expression further, you can see the parameter here is A and B. And in this case, we take A and B to be fixed. It is a fixed parameter. So if A and B are fixed, then we know that if A greater than 0, the distribution of YT will converge to normal with mean 0 and this variance. And this will be easily obtained by studying this term. Because as A greater than 0, in long time, this quantity just vanish. You will only have this quantity, and this will be a normal with mean 0, and variance would be this integral b square e to the power minus 2a t minus s ds. So that will be basically this. Now, if it is less than 0, then actually this quantity will matter. This quantity will also matter, because if a less than 0, this will diverge. So what will happen is that logarithm of mod yt, I am not deriving here, but if you do simple usual things, then you can show that this yt will diverge, and it will diverge in an exponential manner. So this is also something that is known. And if it is equal to 0, then these terms does not matter. Only terms matter is this. Then you can show by the property of Wiener process this results. So this is the case when A is fixed. But instead of taking A and B to be fixed, if A and B are function of this underlying regime process where xt takes values in S, where S is a countable set, it can be finite or infinite, which is the space of all regimes. Then then what we used to know before 2020 are following. Okay, so before I go into this, let's try to say something about this xt process. Xt, this regime process, we assume that it is a S-valued continuous time Markov chain. Now, what is a continuous time Markov chain? So basically, it is a discrete time Markov chain, but the sojourn times at every state is an exponential with some rate. Let's say this way. So if xt is a regularly nice, well-behaving continuous time Markov chain that is ergodic, that has a stationary distribution pi, in that case, so previously we have three results for a greater than 0, less than 0, and equal to 0. So now what we knew before 2020 are following. You still have three different kind of long time behavior of y that is based on the expected drift of A, where the expectation is computed by the limiting distribution of pi, limiting distribution of x, which is pi. So if it is greater than 0, then we know that yt will converge to a distribution. The exact form is not known, but it is known that the tail behavior of that distribution will be either Gaussian type or exponential type or Pareto type heavy tail. That will depend on this particular value, which is the infimum value that A can take in all possible regimes. So if A hat takes value greater than 0, equal to 0, and less than 0, then this long time behavior of Y will have Gaussian type tail or exponential type tail or heavy Pareto type heavy tail. So that was something that we knew from an earlier work, but we do not know exact structure of the limiting distribution. Then if it is strictly less than 0, expected drift is strictly less than 0, then it is a transient state, and it is also known that it will diverge exponential. And honestly, for the critical case, when it is equal to 0, it is only known it is null recurrent. So it is a technical term, null recurrent. I'm not trying to explain what that is because it will take some time. So one can think that it is something that it is not transient, but it is close to one-dimensional Brownian motion type of haphazard behavior. So so that's what we know. But again, there is no explicit behavior that was known before 2020 about this kind of long time behavior of Y. So one of our contributions that was okay. So this is an example on real life data. So basically, this is a S&P 500 data, which is basically the index of top 500 share price in United States share market. And that index, we can see that how that index is behaving from 2010 to 2020. And if you feed a regime switching Ornstein-Uhlenbeck process for two state space two underlying regimes, then one of our computation will actually show, it is not our computation, it is done by Chevalier et al. They actually got these two regimes feed this model nicely, where you can see that This blue part is the case when the Ornstein-Uhlenbeck process is behaving in a transient manner. That means that when A is less than 0. So when A is less than 0, previously we saw that if A is less than 0, that means drift is positive, which means that it will grow, the stochastic process will grow, and that is basically the blue part of the process. And the red part of the process is basically when A is greater than 0, which basically means that the drift is negative. So it is showing that overall, the way blue is switching to red and red is switching to blue, overall expected drift with respect to the stationary distribution of X switching process, that is actually negative. And that's the reason that overall it will have a steady growth. So this is an example. But again, I mean, coming to the original problem, nothing explicitly was known before 2020 about these three different cases, that what how explicitly yt we can have as t going to infinity, that can be expressed based on the parameters of the xt dynamics. So we have some results. Uh, uh, okay, so to explain those results, we need to explain this kind of quantity, and that is called the stochastic recurrence equation. It is an abstract thing, but again, I mean, I'm just defining it so that we can explain certain quantities better. So for two random variables, given random variables A and B, we define that X satisfies an affine stochastic recurrence equation if it satisfies this kind of linear affine equation. X is equal to ax plus b, that happens in distribution, which basically means that distribution of x will be same as the distribution of ax plus b, where x is independent of a and b. So it is difficult to understand, but let's see that how you can see this thing. So suppose a and b are the given two distribution. So you generate copies of AB, which is A1, B1, A2, B2, A3, B3, that are coming jointly IID from joint distribution of A and B. Then you define a sequence of stochastic process, which is like this. And if for some condition of A and B, there exists a stationary solution, then the distribution of the stationary solution will be actually this. Now, the point is that for one dimension, what are the conditions for which this exists uniquely? So the condition is that when expectation of log mod A less than 0, and when expectation of log plus mod B, so log plus means logarithm of maximum of mod B and 1 is fine. Expectation of that is fine. So if this happens, and some apodicity condition very for certain non-trivial cases that are applied, but uh, for most cases, these two conditions will suffice existence and uniqueness for one-dimensional stochastic recurrence equation. So we'll see that how it will show up in the limiting structure of the long-time behavior of one. So yeah, so coming back to the original point, before 2020, nothing was known. Then in 2020, we published a paper in Bernoulli, and that actually suggests three explicit form of the distribution for y for t going to infinity. So for that stable case, when expected drift positive, and yeah, so when expected drift positive, then we actually showed that the distribution of yt will be a scale mixture of normal. And the way scale mixture works is that there is a summation of pi j, and this pi j comes from the marginal distribution of x. But then you have a normal 0, sigma in A, and this sigma has particular measure that is, so basically scale mixture of normal means that you have a mixture of normal where the mixing component is on the variance component, and each normal has mean 0. So you have an explicit structure of the distribution that works like that. And this structure of mu j is actually can be expressed in terms of a stochastic recurrence equation where A and B are coming from some pathwise properties of this X dynamic. So that was the first result, which is nice. And in transient case, we have this particular result that how yt diverges. So it will diverge exponentially, but if I scale it down with square root of t and shift with this quantity, then you actually see that it will be also a scale, it will be also a mixture kind of distribution, mixture of normal, and there will be a sigma j and expected ij. So I'll explain what that is. So sigma j is basically variance of a quantity, and that quantity is basically from tau naught j to tau 1 j, this particular quantity. Now what that is? So tau naught j is the first hitting time of the underlying regime process to state j, and tau 1 j is the second hitting time for x to hit state j. So from first hitting time to second hitting time, how x behaves, and you take that integral with scale by this, and you, since this is a random quantity, because a stochastic process, how regime process behaves from state j and then some other states and comes to state j, so that is not a fixed quantity, it will be a random excursion, and variance of this excursion of this integral path is sigma j square, and that sigma j will be here. And in the denominator, you have expect square root of expected interval length, and this interval length is basically tau 1j minus tau naught j. So that is expected of ij1. So this is something, we have a result where expected drift is strictly less than 0. But what happens, interesting thing that we found that in for equal to 0, when it is equal to 0, you have very similar to the result that is in this transient case, because if it is equal to 0, then this quantity is just 0, so there is nothing here. You have this quantity here. But what happens in the right hand side limit, you have everything there, but instead of normal 0, 1, you have here absolute value of normal 0, 1, which is basically square root of chi-square 1. So that is a quite a strange result, which is something that we have found. So that is one thing that we found this result, and that was for certain type of regime process, which is continuous time Markov chain that has a stationary distribution pi. Yeah, so that was done in 2020. But then again, you still have some type of time series where you cannot actually have, you cannot justify the underlying regime process to be a continuous time Markov chain. And the reason behind that is, if it is a continuous time Markov chain, then each sojourn times to each state will be exponentially distributed. Now, if it is exponentially distributed, then all these blue sojourn times length, that will be sampled from exponential distribution. So basically this blue length, this blue length, this length, and then again this long length, this length. So each of them would be sampled from exponentially distributed. But this is a real life data for BNP Paribas volatility, stock volatility return data, and we feed again a regime switching process thing, and you get this kind of sojourn times. But you see that this particular sojourn time at a particular state is around 7 to 8 times longer than other average sojourn times of blue. And that is extremely rare event if it is an exponentially distributed sojourn times, which is happens when you have X as a continuous time Markov chain. So that basically gives us this idea that what happens that if we use a general sojourn time distribution, and if we do that, then we lose the Markovian property of X. And then we come into the territory of a new kind of stochastic process for regime process, which is called semi-Markov process. And that is entirely a new type of regime process for which continuous time Markov chain will be a special case. Now, I'm not trying to go into that, but I'm trying to say what are the difference that one can have. Of course, there is a practical motivation that if we do from Markov to semi-Markov regime process, then you can have your sojourn times to be non-exponential. But there are also some other types of relaxation and some practical examples where it fits very nicely. So there is a need for similar result for semi-Markov switching, regime switching processes. And again, I know I have 5 minutes. Again, we know that from Markov to semi-Markov extension is not very easily possible because there are some mathematical difficulty and things, other issues are happening. So, but we still did that, and it is not published. This paper is not published yet, but it is under review. So what happens? So I'm not trying to go into details of this nitty-gritty details of this underlying semi-Markov process. What we find here is something that yes, we have similar result, but not quite same. So for the okay, so I'm not. This is the construction of semi-Markov process, switching process, which is quite intricate, and I'm leaving that. And then there are other things. So I come back to the result, and here I just want to mention few things. Unfortunately, when I compiled, initially I have this slide that was looking good, but unfortunately now for this particular laptop, somehow it is the PDF Acrobat Reader is showing this slide in a certain different way, and I'm sorry for that. But if I mention what happens for the stable case, you still have similar kind of mixture of normal type of characterization. But now here you can see that how this mu j behaves, the scale mixing measure that I talked initially about. So this mu j can be represented in this form where you have this red part and this white part. Now red part contains Tj and white part contains Zj. So Tj is a distribution pi j star, which is basically something that I had mentioned in the last slide, but I did not go into the details. So this is basically, you can say that it is a size bias transformation of average sojourn time at state j. And Zj satisfies that kind of stochastic recurrence equation where Aj and Bj are some pathwise functional of this regime process from tau naught j to tau 1j. And then you have this crazy kind of integrals that shows up. So you have a very explicit, nice closed form structure for which you can explicitly express the limiting measure. And then you have for divergent cases, we have same thing, expected drift greater than less than equal to 0 case. But here, instead of continuous time Markov chain, we have 3 types of results. And that depends on whether sigma j square finite, where sigma j square infinite, and sigma j square equal to 0. Yeah, well.
Yeah, I think we have to stop. Maybe one question. We have 1 minute left to the next speaker.
Okay, so maybe I'll stop here. But again, we I will make one comment. So we have similar behavior for each of these 3 cases, but the limiting measures are very different. So yeah, thank you. I mean,
okay,
I can take other questions. Yeah.
Yeah, thank you, Dr. Majumder. We have maybe less than a minute. If there is a quick few seconds question, anyone can raise your hand. Otherwise, I'm going to move to the next speaker because we have to start at 9. Shaule?
Yes, Shaule.
Abhishek, I just wonder how you calibrate the regime process to observe data.
Yeah, so basically it is, you parameterize that, you fix the number of underlying regimes, And then there is a thing called EM algorithm, expectation maxima. You do not observe the latent regimes. You do not observe the A value and what is the underlying, which are the underlying regime the process is on. So basically, there are like, it is called the latent process study. I mean, estimating parameters of the latent process. And what you do that you write down the complete likelihood, try to solve it, and that will be the M step. And then in the E step, at every time you need to do the conditional expectation. So it is the EM algorithm for hidden Markov models or hidden semi-Markov models. Just search with that, you'll get
Okay.
examples of that. Yeah.
So if anyone has question from Dr. Majumder at the end of the next talk, when we are closing the event at 9:45 UK time, there will be the session open for 15 extra minutes. You can ask your questions there.